Why do we need Fourier series? Previously, we studied elementary signals like step, impulse, and ramp. But real-world signals are often periodic, like sound waves, alternating current, and radio signals. Fourier series allows us to decompose any periodic signal into a sum of sinusoids. This is fundamental to signal processing, communications, and many engineering applications. A periodic signal repeats itself at regular intervals. Formally, x of t equals x of t plus t for all t, where t is the fundamental period. The fundamental frequency is f equals 1 over t, and the angular frequency is omega equals 2 pi f. If a signal has period t, it also has period kt for any integer k. The smallest positive t is the fundamental period. When we decompose a periodic signal, we get harmonically related sinusoids. The fundamental frequency is the first harmonic with frequency f0. The second harmonic has frequency 2f0, the third has 3f0, and so on. These are called harmonics. Each harmonic is an integer multiple of the fundamental frequency. This is why musical notes at octave intervals sound similar. They share harmonic relationships. The Fourier series represents a periodic signal as an infinite sum of harmonically related sinusoids. The synthesis equation is x of t equals a0 plus the sum from n equals 1 to infinity of an cosine of n omega 0t plus bn sine of n omega 0t. The coefficients an and bn tell us how much of each harmonic is present. Alternatively, we can write it in terms of complex exponentials using Euler's formula. The aₙ term is the DC component, also called the average value or offset. It represents the mean level of the signal over one period. To find the DC component, we integrate x of t from 0 to t and divide by t. If the positive and negative areas cancel, the DC component is 0. For a pure sine wave with no offset, a₀ equals 0. Let us visualize how a periodic signal builds from sinusoids. Consider a square wave. Its Fourier series contains only odd harmonics, 1, 3, 5, 7, and so on. The fundamental gives the basic shape. Adding the third harmonic makes the corners sharper. Adding the fifth sharpens them further. As we add more harmonics, the approximation approaches the original square wave. This is the power of Fourier series. In this lesson, we introduced Fourier series for decomposing periodic signals. We defined periodicity with period t and fundamental frequency omega 0. We learned that harmonics are integer multiples of the fundamental. The Fourier series expresses any periodic signal as a sum of sinusoids with coefficients an and bn. In the next lesson, we will derive the formulas for calculating these coefficients from the signal itself.